Baby, this is what you came for. Lightning strikes every time she moves, and everybody's watching her, but she's looking at you. You came for. Lightning strikes every time she moves, and everybody's watching her, but she's looking at you. Till they can replay. Who knows why it's gonna be this way? We say nothing more than we need. I say your place when we leave. This is what you came for. Lightning strikes every time she moves, and everybody's watching her, but she's looking at you.
I wanna jam it with you. We're jamming, jamming, and I hope you like jamming too. Ain't no rules, ain't no law, we can do it anyhow. Cause I will see you through. Cause every day we pay the price with a little sacrifice. Jamming till the jam is through. We're jamming. To think that jamming was the thing of the best. We're jamming. Then I hope this jam is gonna last. No bull can stop us now. We neither beg, no we won't bow. Neither can be but no sword. We all defend the right. Judge our children must unite. Your life is worth much more than gold. We're jamming. Jamming, jamming, we're jamming in the name of the Lord. We're jamming, 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 we're jamming right straight from your holy Mount Zion, holy Mount Zion, just seated in Mount Zion, arrows of creation. Jamming, jamming, what you want. I wanna jam it with you. We're jamming, jamming, jamming. I hope you're jamming too. It jumps above my pride. Truth I can't cannot hide to keep you satisfied. True love that now exists is the love I can resist. Down by my side, drumming and drumming and drumming, drumming and drumming and drumming. Hope you like drumming too. Drumming, drumming, drumming. I wanna drum with you.
Jump down the shelters to get away. The boys are cooking up their guns. Tell us, General, is it party time? If it is, can we all come? Don't think that we don't know. Don't think that we're not trying. Don't think we move too slow. It's no use after crying, saying it's a mistake. It's a mistake. After the laughter has died away, and all the boys have had their fun. No surface noise now, not much to say. We've got the bad guys on the run. Don't try to say you're sorry. Don't say he drew his gun. They've gone and grabbed old Ronnie. He's not the only one saying it's a mistake. It's a mistake. Tell us, Commander, what do you think? 'Cause we know that you have all that power. Is it on them? Are we on the brink? We wish it all, throw in the towel. Will not fade out too soon. Not in this finest hour. We saw your favorite tune. We'll send a card and flower, saying it's a mistake. It's a mistake. It's a mistake. It's a mistake.
No limit in the sky if I don't wanna fly for ya. No, I'm a tears in my eyes that I wanna cry for ya. With every breath that I take, I want you to share that air with me. There's no promise that I won't keep. I climb a mountain that's not too steep. When it comes to you, there's Don't be blind. Watch me speak from my heart when it comes to you. Want you to share that. Want you to share that. Keeping it alive, arrow got your name on it. Don't miss hold on alone and regret yourself on it. Open up your mind, clear your head.
To our panel on the use of panel data and administration research. It's a great pleasure to receive today our two panelists that are outstanding scholars. We have today Jason Coupet, who is an associate professor of public management and policy in the Andrews School for Policy Studies at Georgia State University. His research interests include strategic management, data development analysis, performance measurement, organizational economics, management science applications in the public sector, and the political economy of organizations. And his research has appeared in top journals like the Journal of Public Administration Research and Theory, Nonprofit and Voluntary Sector Quarterly, Journal of Transport Economics and Policy, among others. His work has also been covered by the Washington Post, The Conversation, the Wall Street Journal, also among other media outlets. And he's on the editorial boards of the Journal of Public Administration Research and Theory, Public Administration Review, and Nonprofit Management and Leadership. So I'd like first to thank a lot, Jason, for being here today. We're very, very grateful and happy to have you and to be able to learn more about methods and panel data from you. And we have also Vinicius Brei, which is an associate professor of marketing at Federal University of Rio de Janeiro and the coordinator of the chair Tramontina Electric, a visiting scholar at the MIT Media Lab, as well as a former visiting scholar of Harvard University. He researches the intersection of consumer analytics, judgment decision-making, and market dynamics, with special attention to individual and organizational prediction, market potential, and demand forecasting estimation. His research uses a variety of methods from behavioral experiments to machine learning, and his work has been published in journals such as the European Journal of Marketing, Journal of Retailing and Consumer Services, Marketing Theory, Journal of Consumer Behavior, among others. So the idea today is to discuss a little bit. Thank you very much, Brei, for being here with us. It's really, really great to have you here. And the idea today is to discuss a little bit of the possibilities of uses of panel data in administration research. And I'm going to do that from different perspectives. In terms of fields, with Jason coming from a strategy public administration perspective, Brei coming from a perspective of marketing, and also with different types of approaches that will be highly complementary. So I thank you again. And Jason, please, the screen is yours.
Thank you very much. I'm just returning from Sao Paulo, actually. So I learned a few words in Portuguese during my week there, but unfortunately not enough to give my presentation in Portuguese. So forgive me for the English here. Give me 1 minute to get the presentation up. Okay. All right. Can everyone see?
Yes.
Okay,
Yes.
Great. Okay, well, thank you for having me. And I'm going to talk a little bit about panel data analysis and management. And there, at the end of the paper, there'll be a citation where we do, in my opinion, a more thorough job than I'll do today on sort of walking through the trade-offs of some of these models and giving some more practical advice for management scholars who are interested in implementing some of these designs or approaches in their management research. So once again, today's overview will be pretty general. I'll just sort of be talking through some broad research designs and approaches. Each one of them you can do much deeper dives in. They're big literatures of their own. So I'll talk a little bit about the advantages of panel data versus cross-sectional data, and then give a general overview of some research designs that can be, once again, sort of added on and further developed as your research question sees fit. Okay, so in empirical management literature, and this is a case, in my opinion, across the board, general management topics, fields such as marketing, operations, et cetera, strategic management, typically do probably a little bit better job of this than public management. But I think in general, there are a lot of cross-sectional designs. And the reason for that, right, is collecting data can be expensive. And if we're often collecting data ourselves, it can be difficult to go back again and again and again with the same rigor to get data over many years. So they can be, and these cross-sectional approaches can be useful for identifying the relationships that help inform our theoretical development. So, we learn about things that management phenomena that may be connected to each other. The problem is with these approaches is that when it comes to theory and testing theory, the cross-sectional approaches can have limits, right? We often want, in order to better build theory, we want to isolate the phenomena that we care about so that we can say, we know that changes in this phenomenon, we can expect it to cause changes in the dependent variable that we care about. And because cause and effect, right? And because causal inference requires temporal precedence, right? It requires us to say one thing, to know that one thing comes before the other thing, right? What we care about, what we say is the cause should always come before the effect. It also requires that we do a good job sort of explaining away, either statistically or logically, but usually both, alternative explanations, right? So how do we know it's the phenomena that we're testing that is causing the effect that we're most interested in? And so these cause and effect designs remain the gold standard. And in cross-sectional data, because of the temporal precedence aspect and the inability, right? It's hard to collect data on everything, right? These phenomena are also mushy and wide, and we don't have the data that we need to properly control for everything that we, even if we did, right? It'd be hard to know what we don't know, right? So we can use time to address that. So some scholars use randomized controlled trials, and if you can do that, great, right? They're expensive, but they're really useful and sort of remain the gold standard in a lot of social science fields, including management, when we are interested in having the most internally valid design possible. Often, though, what we do in a lab can be difficult to map on to the sort of broader phenomena of broader interest. They often can be just really expensive and often not ethically feasible. Like we don't, of the research questions we're interested in, it's always not ethically feasible to ask the kinds of questions that we're interested in a lab setting. And so research is often used, as you all know, administrative data. It could be at the firm level, agency level, individual level, either of these, right? That we can, and if we graduate these data from cross-sectional, where we have like a snapshot in time, to panel data, where we have snapshots in time of the same units that we observe, right? So we do a study as cross-sectional, we can repeat that over time. It can allow us to establish temporal precedence, but also there's some, because of the nature of if we make some assumptions, and there are ways to test that they're credible, about the nature of data, we can use the fact that we have lots of time to address alternative explanations as well. And so we define panel data here as a set of data that follows the same subject, so individuals, firms, any other unit of analysis, but in management research, often individuals or firms, organizations, over multiple periods of time, right? So we take the same we take the same data, we get the same data, and we get it for, instead of 1 year or 1 month, we get it for many months, right? And so here I'll give some general walkthrough, some brief approaches of a few different sort of groups of designs. I'll talk briefly about some trade-offs, and then I'll wrap up with the citation, and that does a more thorough job here. So how I use panel data, I'll talk a little bit about pooled regression, pooled ordinary least squares. Then I'll talk about what fixed effects are and how we might use them. I'll talk about dynamic panel models, and then sort of refer folks to some other research designs that may help them in pursuit of causality. Okay, so some broad research designs. The first thing that we may do, right, to augment, and so all of this will sort of take the approach of, we have a linear regression, right, where we care about the effect of X and Y, and then there's some error term, right? So in order to prove upon that with time, one approach is to simply pool our data, right, where we would have a cross section and then we just keep going, right? We add the many different years in a pool. And this is an example, a snapshot of a project I have going now, where you can see I've got data for Arizona State University here, but instead of having it for just 1 year, I've got it for multiple years, right? So 1993, 1994, 1995, all the way through 2015. And for every observation in a sample, we have data that look like this. And so then we keep going on our right-hand side, and every variable that we care about, we observe over multiple years. Pooled OLS approaches simply just pool that data, right? So we would take the same regression approaches that we would normally take, except we have multiple years in our X's and our Y's. So we think about just like a regression with more data, right? The challenge with that is that in most firms, right, particularly when it comes to firms and organizations, right, organizations are often path dependent, right? And so what happens last year influences what happens this year, right? And so that means our error terms, right, in our regression, if we were to multiply this out, because we'd essentially be running lots of different regression models over time, like those error terms are going to start to be correlated with each other. The same thing applies to the independent variables. Those will also start to be correlated with each other. The X's will depend largely on the X's before, and these OLS approaches don't account for that, right? Our data are not independent, all right? So one thing you could do to address that in pooled OLS, right? And in Stata, this looks just like your regular regression. Once you tell the command that this is panel data, you do exactly the same thing, except typically you'll want to cluster your standard errors by observation level, right? And so you can cluster your standard errors by firm level if you're doing firm, or individual if you're doing individual. The challenge is this doesn't solve the problem of the correlated independent variables, right? Like, so what happened yesterday influences what happens today. And so our X's are still not independent. Our error terms may be, but our X's are not, right? And so so that's a challenge with pooled OLS, and why you often don't see it used much by itself. It also doesn't address the problem of unobserved heterogeneity. So we have the same problem that we have with other regressions, in the sense that, okay, so I collected data from 5 variables, but in these complex phenomenon, there may be 20 other things that affect both our X's, the data that we collected, and the outcomes that we care about, right? And so how do we know if it's what our X that's causing Y relative to any of the multiple other factors that that could be there? Right? So it's our shark bites and ice cream problem, right? Pooled OLS doesn't address that, and so when you see pooled OLS designs, you often only see them in rigorous approaches. You often only see them if the X variable is randomized, right? If through some other way I can establish that the variance in our independent variables is random, right? I sort of then I can know it's independent of any other process other than the process that randomly generates X. You often not see pooled OLS approaches used because they have the same sort of challenges involved, same sort of challenges as other regressions. So in order to address this problem, you'll often see researchers add fixed effects to their models. And so you can think about fixed effects models as regressions with a dummy variable on the right-hand side that indicates the status of that status as that unit of analysis, right? And so In my case, I have a set of American universities, right? Arizona State University, Georgia State University, et cetera, et cetera. And let's say I have 50 of these in my data set, 50 organizations. With our fixed effects, we're simply adding an independent variable that is 1 if you are Arizona State, 0 otherwise. 1 if you are Georgia State, 0 otherwise. And so if we have 50 firms in our sample, we'd essentially be adding 50 independent variables on the right-hand side, right? What this does, this is a very common approach. What this does is that it addresses, right? You're controlling for status as that firm. And so what that does is any phenomena that may be correlated with that firm, anything unique about that firm, the fixed effects approaches control for. And so we can go a long way towards establishing the cause and effect with X by just controlling for all the other things about that firm that don't change over time, right? So they do a really good job with addressing time invariant endogeneity. And in management research, you see this done a lot because right, firms don't change very much, right? You have shocks, but there's a sort of inertia to typically how firms work. And so a lot of what we explain in firm behaviors can be captured in a control variable for that captures sort of status as that firm, right? And so you can get the challenge with fixed effects. Anyway, before I talk about challenges, you can see how this might matter, right? Like what we do here, again, is essentially because we have that control, we're saying, what is the effect of X on Y, right? Controlling for status of that firm. We're basically just looking at the variance level in each firm over time, right? And so you can see how that might matter in this graph here, which I pulled from a paper that I'll cite later on. If you look at that line that says random effects, or you can think of random effects in this case as pooled OLS, like they're really similar if a set of assumptions are met. We have like this dotted line here could be like a regular regression line of the effect of X on Y, right? Let's say we're interested in the effect of a size of a nonprofit on its performance, right? Sort of just generic performance thing here. And we can say, as they get larger, right, they tend to perform better. Let's imagine that this is something we observed. What fixed effects does is takes these data points and dots and says, well, if we address what is unique about each individual firm and only look at the variance, you may find sometimes a very different relationship here, right? Where we have these gray arrows, we say, all right, well, what about the trend lines that are just looking at the variance in firms over time because we have that control, for presence of that firm. You can get different effect sizes and in different directions. And so you often see, like if you just run a regular regression and then add fixed effects, the results will be very, very different, right? Because again, we're controlling for all these other factors that we otherwise wouldn't be. The challenge with fixed effects, right, is they don't address time invariant phenomenon that should be controlled for, right? So firms typically don't change much, but they can change in often imperceptible ways that we want to be able to address if we care about isolating our causal inference, right? We want to be, to as reasonable degree as possible, confident that X caused Y to better test theory. And if there are other things that are changing, even if we have that fixed effects in there that we can observe, fixed effects doesn't, by itself, adding fixed effects doesn't address that. I should say, you can add fixed effects that are not firm level fixed effects, right? You could have the same thing you can control for states or the state that they're in, or if this were Brazil, for instance, we say, all right, we're going to control for whether or not a firm is in Bahia versus Sao Paulo, right? So we want to know, we say, the things that are unique about these states, maybe a different business climate, different organizational climate that we can control for. So we can back those fixed effects out to any level. Either way, though, it doesn't matter if there are if there are lots of things that change over time with respect to individual firms that we can't see. We also have this problem, right, that sometimes in panel data, like our dependent variable, so let's say performance, can also be path dependent, right? So our performance today, right, is to some degree a function of our performance yesterday, right? And so our fixed effects don't always do a good job of controlling for that. They can introduce nickel bias, something we elaborate on in the paper more. And so sometimes we need to model this in a way that doesn't compromise the rest of our results. And so to address that, there are dynamic designs where essentially you can think about a dynamic design, same thing as a regression, right? With our fixed effects, and how fixed effects are added differ based on what kind of design you use. And all we're doing here, right, is we're taking that dependent variable and we're sticking past values of it on the right-hand side, right? So we're saying, let's stick yesterday's performance as an independent variable, right? And these approaches have lots of different ways to model the assumptions that they take. All of these have different robustness checks, and we elaborate on these in the paper. But what's nice about these dynamic designs is it addresses that path dependence in your Y, so that we can be reasonably sure that we're controlling for the effect that the dependent variable from last periods has on what we do. Now, each one of these, you might notice, get progressively expensive, right? Because we keep adding things to the right-hand side, right? We're losing degrees of freedom. And so we'll need our samples to be bigger. We need to make sure we have lots of variance. So there are costs to these, right? Just like there are any other model. As you want, there's this sort of an inevitable trade-off with administrative data. Often, unless we have really nice experiments or quasi-experimental designs, often just the more we add, right, the better we get at internal validity. We need more data to better model that, to make sure that those standard errors don't keep going up on us. But there's some standard dynamic designs that I think are useful. There are a set of them called Arellano bond models. There's system GMM. And again, in the paper, we elaborate on these and provide some places to get some additional information. You could teach an entire class on just on system GMM models. And so the upside is as we continue to get more and more precise estimates of our effect sizes, often if we have a nicely specified model, we're starting to talk about just sort of minute changes in beta, right? And so I wouldn't lose any sleep necessarily about getting anything wrong, but these do get more and more precise as we sort of add these approaches, right? So we've got our regression-based approach, and we've got fixed effects, and then dynamic designs. So all of these approaches, I'm going to wrap up in a second, do a good job controlling for unobserved variables. And they get us closer to causality because we can stash fixed effects in there. We can also capture it by putting a Y, which controls for everything that affects Y, that is not time invariant, right? But they don't do so perfectly, right? Particularly if we anticipate that organizations may experience other shocks that may affect performance. So let's say, back to our example on like the effect of size on performance. We can control for lots of things and isolate size, but it may be hard to know, particularly if we don't have data on this. Like, what if the organizations that got bigger were more likely to have a change in CEO, right? If we can't observe that, we've got this unobserved factor that is changing along with the thing that we care about. And these approaches don't necessarily capture those, right? And so they don't do so perfectly. And so like in journals like Management Science, you'll get feedback that says like, hey, nice job. Hopefully, if reviews are nice, like nice job controlling for other things. However, we're not sure that this is cause and effect. So often what you'll see is each one of these approaches used in conjunction with some other process that generates a random independent variable, right? So you'll often see researchers take advantage of some exogenous shock, some other process that we can say, aha, now we know our independent variable is happening independent of some other process. And these controls with the dynamic model still have the same effect, dynamic and fixed effects. So we're saying we still want to do a really good job controlling for other things that may exist about the organization. And so you'll see fixed effects used a lot with other designs like difference and difference, or instrumental variable approaches, which use other processes to generate an independent variable that we can be reasonably confident is random, right? And by random, we mean sort of uncorrelated with things that we can't see, right? And so that's a basic rundown here, just to sort of introduce these panel data approaches, and you'll see them used throughout management literature. Increasingly, though, you'll see them used alongside these more randomized processes. For more a little bit more in depth of an analysis, we along with my former students and I, they definitely took the lead on this paper. We did a walkthrough of these different designs intended for nonprofit management, but generalizable to general management mostly as well. We also include a hands-on walkthrough, some state of code, a data set, so that folks can sort of take these approaches as well and walk through them. There are other resources too that I'd be happy to share with folks to help walk through stuff that other people have written and other nice accessible guides. So feel free to email me with questions as you approach these. But that's a general rundown. I hope that was useful, and please take a look at the paper that we cite there for a more thorough rundown. Okay, I'll stop there.
Thank you very much, Jason, for this very, very clear and useful introduction to the possibilities of use of panel data models. And now I invite Brei, please. Thank you again for your presence, to evolve on a complementary approach more on the machine learning side.
Thank you, Rafael. Thank you for the invitation. And thank you, Jason, for the insightful talk. It's great to be able to learn from you. Thank you for the opportunity. Let me share my screen. Please let me know if you can see my presentation. Okay, good. Okay, so I will take a different approach compared to Jason's. He focused more on the design part of the panel data. And more specifically, he focused on linear ways of dealing with this type of data set. I will use a different approach here, and my approach is based on a simple idea that usually life is not linear. Although we pretend that it is, we analyze it as if it was, but usually it's not. So what can we do about it, and how can we analyze this data when not most, but maybe many of the phenomena that we are dealing with is not linear? So my goal here on this very quick talk will be to analyze how to analyze this type of data when it's not linear, and especially I will be talking about some recent developments in machine learning models that can be used to analyze panel data. And also I will be talking about how to interpret some of these models, because as we are going to see, there is also a trade-off between accuracy and interpretability. And this is a very important issue when we are dealing with nonlinear models. The big advantage about linear models is that they are very explainable and usually they are interpretable. So I'm going to discuss these issues during this short talk. So very, very broad view about machine learning for those who are not familiar with this literature. So machine learning, most of the authors would divide machine learning in 3 different types: the supervised learning approach, unsupervised, and reinforcement learning approach. Mostly, I would say that most of the applications that we see nowadays are supervised learning approaches. And I will be talking about most of these, some of these algorithms of supervised learning approach. The big idea about machine learning is usually generalization. And how is it done? Usually we have a data set, and we split this data set at least in 2 groups: train and test. Sometimes when we have lots of data, we might split in a validation set, but usually the traditional machine learning approach will be to divide or to split the data set into train and test. The problem with machine learning is that sometimes we are dealing with, machine learning is very good to generalize, to predict, but we are not always concerned about cause and relation effects, about explanatory issues. That's exactly what Jason mentioned, and this is a very important aspect of panel data, because with panel data, we can deal with causality. We can understand causal effects, and this is something that sometimes it's hard to deal with machine learning models. Why? Because there is a big trade-off in machine learning algorithms, and this big trade-off is accuracy and interpretability. If we see the broad range of algorithms that we have nowadays, and this is a very, now I want to make sure that I want to reinforce that I'm not saying that these are all the algorithms that exist. Of course, we have hundreds of different algorithms. These are, I would say, mostly families of algorithms that we have. On the right side here, we can see, for example, the type of algorithms that Jason was describing, linear models. Linear models, usually, they are very interpretable, easily interpretable. We know exactly what a parameter is doing on the model. We know what each parameter is doing and how is it doing. So for example, the dummy variables that Jason mentioned, we know exactly how they are doing, what is their role on the model. It's very interpretable. The downside is that sometimes they are not as accurate as the recent nonlinear machine learning models, such as deep learning, ensemble models, and Bayesian models. What we ideally want is on this almost impossible goal of having a high accurate model and high interpretable, which is, of course, very difficult to reach because as we are dealing with a trade-off, we are almost never getting both positive aspects of accuracy and interpretability. So in this very short talk, I will be talking about a complementary review of what Jason mentioned. He mentioned mostly linear models, so I'm going to talk about mostly non-linear models, especially deep learning, ensemble methods, and Bayesian methods. I will not be talking about support vector machines, which is a very interesting algorithm that has been developed in the 1990s. But now I would say that it's not so common. Its use is not so common because we have deep learning and ensemble models that are outperforming support vector machines. And I will try also to give a very broad overview about Bayesian models, which is, in my opinion, the future of the field. I will be presenting next week one paper about how Bayesian models could strengthen marketing science and how frequentist models have jeopardizing reproducibility in science in general. So I will try to talk very briefly about it. So let me get started with deep learning. Very briefly, deep learning we can see this idea of neurons that connect themselves in different ways, and we have an input layer, we have hidden layers, and we have an output layer. Deep learning is a very flexible algorithm because it can be as simple as this one, which could be classified as a shallow learning. But when we have more layers, we can have many different architectures. So what is interesting about deep learning is that we can tailor the algorithm to specific needs that we have in mind. So for example, we have many different aspects that we need to decide when doing analysis using deep learning models, such as, for example, how many layers are we going to use, how many, what will be the input layer, what type of data, and this is interesting for panel data because we can use either quantitative or qualitative data using deep learning. It's a very flexible algorithm. We can specify how many hidden layers, depending on the complexity of the problem, it might require more hidden layers. The output layer, it can be binary, it can be continuous, it can be multinomial, so it's very flexible also in terms of output. We can specify the type of connections among the layers, how many neurons in each layer. The more neurons, the more complex it will be. Which loss function are we going to use as a measurement of error, for example, which optimizer, how to make this architecture more efficient. And finally, we can also think about the success metric, which will be our final goal to understand, for example, the causality aspects of the problem that we have in mind. In short, this is a very broad overview about deep learning to say that it's very flexible and we can use deep learning in different ways for different purposes. Specifically for panel data, we have two types of deep learning that are mostly useful. These two types are the CNNs, one subfamily of deep learning, and RNN. So CNN is convolutional neural networks and RNN are recurrent neural networks. Why are these two types of deep learning interesting for analyzing panel data? The CNNs are very interesting because it's a very flexible way of dealing with different types of data. For example, it was originally developed for computer vision problems, and we can create different types of layers for different perspectives, not only for imagery, but also for text processing. So CNN is a very flexible algorithm that we can specify the hidden layers in different aspects, in different ways to process text, image, data, what different types of data, whatever we want. So the other types of algorithms that are very interesting for panel data are the recurrent neural networks, or RNNs, as they are usually called. Why are they interesting? Because RNNs, they take into consideration the time aspect. So whenever we are doing any forecast or whenever we are doing analyze of our features or variables as you want, this is something that you're going to find in machine learning literature. Since it comes from computer science, people will mention variables, we will label variables as features, we will name variables as features, but they are synonyms, of course. So what is interesting about the RNNs is that in each neuron, we take into consideration the input data, and the output data also has a recurrent path that takes into consideration the past of the phenomenon we are understanding. In other words, if we take the time t as our input, whenever we take the time t, the neuron that we are analyzing will consider the previous state of the phenomenon. In other words, if we are studying firms or consumers, the current time will take into consideration the past time. So this is why it makes RNNs interesting and useful for panel data, because it takes into account the past into the analysis, and therefore it controls for time series. So this is why deep learning and these specifically subtypes of deep learning are interesting for panel data. The downside about deep learning is that it can be very complex because we don't know exactly how the parameters in each of the parameters of each neuron are calculated. So the positive aspect is that we can include in our predictive model fixed and random effects, but the downside is that it's hard to interpret each parameter as we can interpret on linear models. So this is one of the three algorithms that I've proposed that I wanted to talk about deep learning. The second type of algorithms are what we call ensemble methods, which are not exactly one type of algorithms, but a combination of more than one type. So we have the basic idea about ensemble methods is we have the data set and we analyze this data set using more than one type of algorithm. We combine these algorithms and make predictions, a combined prediction using two or more types of algorithms. There are different ways of dealing with ensemble methods. The most typical ones are unweighted averages or weighted averages. So for example, let's pretend that we are using a decision tree algorithm here. Then we can combine the results of the decision tree with any type of non-linear model that, for example, a quadratic discriminant model. And we can use even a deep learning to combine. Depending on how specific is the problem. So if we have decision tree type of problem, we can give a more weight to that specific algorithm, and we can give less weight to the other types of algorithms. This is one way of dealing with. So we are combining, summing up each of the results and trying to reach a final result. The other way of doing this combination is to use what we call a second level algorithm, where we are not necessarily summing up, but we are combining them, sometimes multiplying, using an interactive way of dealing with these different results. And we are creating what is called a super learner, which is a combination of the previous algorithms. So this is another approach, a different approach. What are the interpretability, before talking about Bayesian, what are the interpretability challenges of deep learning and ensemble methods? First, there is the idea of transparency, which is usually labeled as in two different ways, white box and black box models. So a white box model is what is, for example, it's very simple to understand. Let me just pretend here that we have a simple model that we are trying to explain sales based on, for example, TV advertising. So when we get, for example, the red dots here could be understood as cities, for example, and we can easily explain this model considering the parameters beta 0 and beta 1, and we can calculate them. Our feature here is TV advertising. This is what we want to explain. And we can use OLS or any other linear method. This type of model is very simple to understand because we know exactly the effect, what is the intercept, we know what it represents, we know exactly what the slope represents, and we have a clear view about what's going on. When we talk about black box models like machine learning, like deep learning models, we don't know exactly what's going on inside each of the neurons because each of them has its specific weight, and we have a lot of interactions between the input features. This makes this type of model what we call a black box because it's not easily interpretable. If we take, for example, the state-of-the-art deep learning models for natural language processing, for example, like GPT-3, or this year there is a new one that is called Bloom. It has something about 175 billion parameters. So it's something that it's infeasible to understand each of these parameters. That's why they are called black box models. They have a very good results in terms of forecasting, but we don't know how to interpret exactly each of the neurons and what they are doing for the model. That's why we have what is called model agnostic methods to interpret these black box models. So basically, we have three types of interpretable methods. Those that explain the overall behavior of the model, some methods that explain individual predictions, for example, consumers or firms, why are they behaving like the way they are, and methods that combine both aspects, global model behaviors and individual predictions for consumers or firms. It doesn't matter the unit of analysis that you are working with. So there are different types of explanatory methods. I'm not going into these details. I have the reference, and I'm going to include, I will make sure to include the reference at the end of this presentation. So for those who are interested on understanding interpretability of machine learning models, which would be the best way to go, I will focus on only two types for this short presentation, which are the local surrogate models and the Shapley values. So these are ways of interpreting black box models. So let me go through briefly these two ones. So the local interpretable model agnostic explanations, this model was developed in 2016, and it's very interesting because we can take, for example, one specific person or firm, and we can understand why he, she, or it is behaving the way it is using the features of the model that we have. So we have different variables. We can include here fixed or random effects, and we can understand the role of each of that fixed or random effect, the role that it had on the behavior that we observed for that specific firm, for example. So it's a very interesting algorithm because it can identify easily and clearly the role and how each feature affected the behavior or the outcome that we have. The other family of algorithms that are really useful for interpreting deep learning and other black box machine learning models is the Shapley value. So the Shapley value is based on the game theory, on game theory, and it understands or try to clarify the payout among different features. So instead of thinking about each individual firm or each individual consumer, for example, and understanding how the features of the model explained or affected the behavior of the firm or the consumer. In this case, we are trying to isolate the effect of each feature level on the final outcome. So, for example, let's pretend that we are trying to predict the price of an apartment. So we can have different features, like if it's in a building, if it's a house, we can think about number of rooms. We can think about if it has a garage or not. So each of these features has levels. So for example, we can think about a building that does not accept pet and the other one accepts pet. The Shapley values, we can isolate not only the feature of, for example, if it accepts or not pets, and how much that specific feature contributes to the final outcome, which is, in this case, the price of the apartment. So Shapley values does not study individuals, it studies final outcomes, how each feature and each level of that feature explain the final outcome. So it's a very flexible approach and interesting to understand complex problems when we have different variables with different levels. Each variable has different levels. Finally, let me talk about Bayesian models, a very broad overview about how Bayesian models can be useful for panel data. So very broadly, Bayesian models are the one specific way of dealing with uncertainty. So the big advantage about the Bayesian approach is to measure uncertainty. How is it done? So this formula is the model of Bayesian approach, and what we want to know is what is called the posterior distribution. As we are dealing with uncertainty, we will be dealing with a measurement in using a probability. So this probability is measured by what we call a posterior. And how do we calculate the posterior? Based on two aspects. First, what we call prior, which is the previous knowledge that you have about something. So for example, when we have a time series, a prior can be the past state of a firm, for example, the prior profit, the prior level of knowledge, level of competence, or whatever you are studying. Then you have the likelihood, which is your distribution of probability based on observed data. So multiplying the prior and the likelihood, we get the posterior, which is the explanation, or the probability explanation about the future. Visually explaining this phenomenon, so usually we have a prior belief about something, and then we get evidence, this kind of green, light blue mixed line here, the prior beliefs. We collect data, which is the evidence, and basically multiply the prior and the evidence, we get the posterior, which is a more precise way of dealing with uncertainty. The good thing about using Bayesian for panel data is that we can use the posterior as a future prior. In other words, we can always update the data as time goes by based on new evidence that we get. The more evidence that we get, the more precise will be the distribution of the posterior and the less error we are going to have. I believe that Bayesian approaches will be will be more and more used because the problem with Bayesian analysis usually is a computational aspect, because we have to make integration about prior beliefs with evidence to get the posterior beliefs. And this is very hard to do if we don't have computer power. Nowadays, we have some very good libraries in Python and R, RStan, or in Python, PyMC. We have very good resources to analyze panel data using Bayesian approaches. And I believe that this is something that we are going to see more and more. So finally, the key takeaways for this very short presentation is that when we think about nonlinear models for panel data, there is no free lunch. This is a node theorem of machine learning. This means that there is not one algorithm that will be always the best one. It doesn't matter the condition. So in other words, we have to test different ways of dealing with panel data and try to see which algorithm presents the best accuracy and interpretability. And remembering that it's a trade-off, we are not going to have the best of both worlds. We need to understand what is more important in our case. Is the prediction itself, or is to understand, to interpret, in other words, the causal effect that Jason mentioned. So if it's the causal effect, sometimes we are not going for the deep learning models. We need to go for more interpretable approaches like decision trees, and maybe more advanced decision trees like extreme gradient boosting, or that are currently the state of the art for decision trees approaches in machine learning. Also, machine learning is a very powerful tool for panel data, but as I've mentioned, the trade-off is the big problem. So we always need to think about what is more important to us. Is it to understand causality? Then interpretability will be the issue. So we have to think about how to do that. I've mentioned that families of models to understand that can be used to understand or to interpret machine learning models. The two that I've briefly explained, the Lime and Shapley values, can be very useful for interpretability issues. But overall, machine learning will be very good for accuracy, but not so much for interpretability. And finally, the Bayesian approach, I think it's very interesting, especially when we have time series and we can always update our beliefs about what's going on in the model. So Bayesian approaches are very useful when we want to measure uncertainty and when we have some knowledge about how that specific phenomenon behaves in terms of distribution, probability distribution. Considering that this session is being recorded, I included all these references for those who want to go through different things that I've mentioned today. I don't want to go through one of them one by one now, but you can simply pause the video and take a look. And I highly recommend some of them, like this Monar's book about interpretable machine learning. Also, I really recommend this Susan Atte's paper about ensemble methods for causal effects in panel data. She's a very good researcher about causal phenomena. So you can, these are a few of the references that I recommend for those who are interested on those models. Well, I think I reached my time, and I'm very grateful for the invitation, Rafael. Thank you so much. Thank you, Jason, again, for the opportunity to learn from you. Thank you, guys.
Thanks a lot, Brei, for the very enlightening presentation, the opportunity to learn really a lot about these methods. And I would remind the audience that you can send questions freely on the chat that I will forward to the panelists. And I'd like to first invite some debate between Jason and Brei. And if you want to discuss a little bit like the complementarity of the approaches, the applicability of the approaches in different contexts, and if you want, I can also motivate that with some questions. If you want just to start asking each other, please go ahead.
Let me say thank you very much for that presentation. That was great. I guess my first thoughts are mostly about how correct you are. I think I know our department here is moving in the direction of more towards these accurate predictive models, because we have so much demand in the public sector for how to use, how to turn unstructured data into structured data, and B, like then having big amounts of unstructured data, structured data, how to use that for predictability in decision making. So I think you're right. There can sometimes be trade-offs between predictive accuracy and causal inference, but if theoretical testing is not paramount, which I think it seems less and less so. I think more and more folks are moving towards these predictive designs that with more precision allow us to make better decisions. So I thought that was a great presentation.
Thanks a lot. Thanks a lot, Jason. There are very interesting challenges that we are seeing nowadays about using these models for public policy and for other types of decision making that I think are important issues that, for example, in the US, I'm sure you're familiar with the credit scoring, the idea of credit scoring, and also there are algorithms, deep learning algorithms that are being used for the justice system to calculate how many years, for example, someone would be in prison. And these are very debatable issues that take into account deep learning models, but they are some of them are black box models, because you have a credit score, but it's not very clear what made your score be like 400 or 600, and this affects your life very much, because this will affect the insurance you pay for your car. This affects if you're going to apply for a loan or something. So this idea of causality and explanatory and explanation is so much important, because it's affecting our lives more and more. So I was very positively impressed about your paper, because your paper discusses this idea of causality, and this is something that usually when we think about science, we are always concerned about causality. But usually when we think about the practitioners, we think that they are only concerned about results. But this is not true. Actually, people's lives are being affected by algorithms more and more. So I think we more and more will be challenged to explain why these algorithms are predicting the way they are predicting things like the ones I've mentioned, like a prison number of years that someone is going to be in prison, or credit scoring. So for these aspects, panel data is very important, because we can use this type of data to isolate the idea of causality, which is something that is going beyond the academic circles and going to our daily lives more often. So thank you.
Great, thank you, Vinicius and Jason. And now I have one question from the audience that is, I'm translating it from Portuguese from the South. It is saying, tu recomendaria. So I'm gonna propose it first to Vinicius. If you would recommend always like a white box model because of safety and transparency in explaining the results. It's a question from Graziele Kemmerich da UFRGS.
Well, thank you for the question. The thing is that white box models are always applicable, but sometimes they are not as accurate as the deep learning models. The idea here is that if we follow the no free lunch theorem of machine learning, we should always try to use different types of models to compare their performance and then decide what to do. So again, in the ideal world, we would have both in a high result of both accuracy and explanation. But in the real life, we never get the best of both worlds. So we need to choose. That's why there is no such situation as an ideal way of dealing with things. And I try to be skeptical and I try to recommend to my students to be skeptical about methods. We should learn different methods, know how to use them, and use the ones that are appropriate for our case. I think it's bad when you consider yourself like I'm a econometrician that deals only with regression models. So I don't think this is a good approach for career development, especially. And of course, to explain phenomena in general in science.
In line with that question, I'd like to pose a question for both of you. That is, there's this trade-off between understanding and predicting with accuracy, between causality and the accuracy of prediction. How do you feel, and then Jason in the area more of strategy and public management, and then Brei in the marketing area, how do you feel that these fields are evolving in terms of how open journals are to publishing each one of them, which would be easier at this moment if there's some types of specific subjects that might be more prone to more predictive models or to more explanatory models? How do you feel about it? Jason, maybe you'd like to go first?
Yeah, I can, mostly speaking for public management, I think that folks are open to both. The discipline, to the extent you can call it a discipline, the discipline is growing empirically so much with regard to design. We're really in the space where we're moving past thinking about organizations with these static sort of cross-sectional surveys, even surveys that are panels, right, where you got to worry about response rate and whatever, into these designs that either do a better job with causality or with predictability, right? Like the ways that we're, right, so we have more, we've got more causal inference in public management, and we have more, much more openness towards deep learning and machine learning algorithms in public management too. I mean, in fact, we're hiring right now for a full associate or full professor that can sort of help take leadership in both. So I think our journals are just at a stage where, you know, if you can help push the discipline forward empirically in either direction, I think particularly our leading journals are open to that. So I think if you do either, as long as what the improvement is clear. So I think we're in the stage where we're benefiting a lot from models that say, hey, we used to, from papers that say, hey, we used to do it this way. Here's this new approach, right? That may improve either the precision of our data, the speed of our data collection processes, or better inference. It's sort of, we're open now, if that makes sense.
Yes, okay. Thank you, Jason.
For a marketing perspective, Rafael, we are seeing, so we have always had surveys as a very traditional method in panel data. And the gold standard nowadays has shifted in marketing a lot from laboratory experimental designs to field studies. So we are seeing more and more field studies, which are much more challenging to run. So there are different tools that marketers have used to study phenomena and also in academia and in industry. So for example, people use a lot Mechanical Turk as one platform of collecting panel data. The problem with this type of data is that the workers, let's say the workers are almost professionals, people that make a living answering surveys and stuff. So you don't have real people, you have professional workers that are so focused and specialized on making money answering surveys. So this was maybe 5-10 years ago. People use it a lot, especially for behavioral research. And we are seeing nowadays journals very skeptical about this type of data set because of the artificial aspect of it. Let's say you are not dealing with real customers, you are not dealing with concrete situations that most people would face in their daily lives. So the more common approaches that we are seeing nowadays in the top journals in marketing are combinations of methods. So we can start to understand the causal aspect using a lab study, and then you try to see in a field study if it really happens, because on the field study is very hard. It's much harder and sometimes almost impossible to run a causal study. So usually you're going to understand you will try to develop a counterfactual way of understanding what's going on in terms of causality on the field. So the combination of lab and field is nowadays the gold standard in marketing. Most of the journals are requiring you can still do lab studies to understand causal effects, but usually the reviewers will ask at least one good field study to prove what you're trying to say. So yeah, this is how I would synthesize how marketing is dealing with.
Thank you, Vinicius. And in line with that, we have here another question. Would it be reasonable to think of machine learning algorithms as tools that can help researchers in identifying patterns and or variables that may be related to a phenomenon, like an exploratory approach, and then test eventual causal effects with panel data regressions? That is, machine learning would be an exploratory tool whose results can be further tested by panel data.
Vinicius, maybe it'd be good for you to take the first.
I can start, Jason. Well, it's an interesting idea, and I would answer that. So basically, if I understood the question, is should I start here or there? What should I do first? So my answer is what is more important for you, accuracy or interpretability? If for you is more important interpretability, then you should start with a regression approach or a more straightforward approach that you can easily interpret what's going on in terms of parameters, estimated parameters. If your goal is accuracy and have a less error or better predictions without taking in so much into consideration or without so much concern about the reasons of that results, then you would go for a machine learning approach. The combination of them is always interesting, but sometimes it takes a lot of work to do them, because especially the deep learning methods, they take a lot of time. There is a lot of pre-processing. If you are to go for a Bayesian approach, it's even more complex because sometimes models don't converge. So each algorithm will have its pros and cons in terms of requirements and development. The gold rule would be try to go as simple as possible. Try to go as simple as possible. If you have good results with a regression approach, stick with it, and that's going to be good enough. You've mentioned something about using machine learning as an exploratory approach. I would say yes, it's possible, but sometimes it requires so much pre-processing and work for running just as an exploratory approach that I don't think it's really a recommended path. So yeah, I think this is my thoughts about that. Jason, not sure if you have any other ideas about it.
No, I think that's right. I'm not a machine learning scholar, but I think the way I think about these things, it depends on what your goal is. If your goal is more what, then, getting the most precise description of the phenomena you're interested in seems like it would be paramount. And so you would want a better model that using these machine learning tools. If you're more interested in why, which is often more a logical question than it is a statistical one, right? We're using models to make judgments about reasons for things. And I think if that's more, you're going to inevitably want to do something more causal anyway. The challenge with that, even if you have a good model, the data that we sometimes generate are not very good. So maybe there's some combinatory, right? Can we get better prediction? Can we use prediction to help generate better data? I think maybe, but I think mostly it depends on what you're after. If it's what, then you'll want to use these more precise machine learning tools. And if you're more interested in why, then you're going to inevitably end up having to do some causal logic anyway. So it's what versus why to me is how I see it.
Thank you, Jason and Vinicius. Based on that question, I forgot to mention was from Leonardo Pila. I would ask a follow-up kind of controversial question that is, I think that his point is in some way going to a process in which we end up with a causal explanation and thinking from a theoretical perspective, thinking about academic work that's not necessarily guided towards solving a problem, but towards understanding some kind of, at some level, some kind of phenomena. Is the predictive analysis somehow an end in itself, or there's a natural path from there to try to understand some causality? That I think that somehow goes a little bit in the direction of his question. No, is there room, as you see now, for us to stop some kind of research question or research discussion just with the prediction, or you feel at some moment we should go to explanation and to understand causality?
Can you start that, Jason?
Yeah, sure. I think sometimes both approaches can be useful for theoretical journals. The way I think about it when I'm asked about this is prediction in of itself for I think absolutely sometimes, right? Like climate change, for instance. Mm-hmm. I think it's really useful to say there we have lots of data that are collected iteratively at different time intervals across the world. And so having an accurate measure of the degree to which something is changing is a very, very useful, approach, even theoretically, right? We having a precise estimate can tell us a lot about what the benchmark should be and when other problems kick in. And so I think it can be. I think if you're more interested though in the why, to me it's the why, right? That we go back to when it comes to causality. I think why there'll be room for that even when data are imprecise or models are imprecise, is because that helps us test theory that already exists. And so to me, they're both useful. It just sort of, even academically, so I think having machine learning approaches can be an end to themselves when the question bends itself well to it, right? Like for instance, we study diversity in management a lot, but it can be very difficult to understand. For instance, what kinds of organizations are more likely to promote or hire members of diverse backgrounds? Having a theory that explains that is really hard to test, right? If we don't have a good understanding of the layout of the world, of the universe. And so in my mind, a paper that lends itself to convincing evidence about the kinds of organizations that I mean, because we can do that badly with regression too. We slap a regression on there and we say, oh, these kinds of organizations, we have a logit model and we have a kitchen sink approach to the right-hand side, but it's very imprecise. And we have lots of papers that are like that. So in my mind, a precise model of the what, right? What kinds of organizations are more likely to promote women, for instance, that will be a big improvement over the way we typically do our diversity management. So to me, it's about, like Vinicius was saying earlier, like sort of defining your question well and being able to use whatever tool is necessary to convincingly make the point that you're trying to make. And so to me, if it's what then those predictive models are still often big improvements over how we typically do things, particularly when we have these poorly specified logit models that don't allow for an accurate representation of the layout of the world.
Rafael, my feeling is that the level of maturity of a field will define the idea of interpretability and causal and what is more important in terms of prediction and explanation. So let's consider, for example, COVID. The beginning, it was really important to see, like try to avoid deaths. So we are trying to predict how we could avoid that, but we didn't know exactly why and what was the mechanism that the disease, how it happened and why it happened the way it happened, the way it was. So in the beginning, the prediction sometimes is more important, but as we go through and as we develop knowledge about something, the explanation of why it becomes more and more important. So science evolves in this way. We may be in the beginning, we may have some good outcomes in terms of prediction, but we don't know exactly why we are getting those results. As we go into the details and we go deeper into the mechanisms that are going on, and then panel data is very important for that. We can try to isolate the fixed, the random, or sometimes the combined effects that are explaining those initial predictions that we didn't know why they were happening. So these are my some quick thoughts about that.
Great, thank you, Brei and Jason, for the very deep and inspiring responses. And we are now going to the last minutes of the panel. And I like, if possible, to talk a little bit about data sources so people can have in their radar where they could get data sources, where they could search for data sources that could be like panels in your different areas. I think that that's important. So that sometimes that's like an important limitation. You don't do panel data because you don't find where this data is.
So most of my work is in, it's just a good question, is in public management and less strategy. So our, increasingly, I think government agencies are getting better about being open and using open source data. So often from a public manager perspective, I know in the US, pretty much every federal agency has regularly maintained panel data that, to different degrees of usefulness and cleanliness that researchers use. But often, I think even, so if it's not public sector, I've had a lot of success, some success, asking managers at nonprofit organizations, or as firms get better about having teams that work with data, about the availability of panel data. And so I got some data about startups that universities are trying to put together from a data manager at my university that collects a panel of what other universities are doing. And so sometimes it's about asking for it. I don't know how helpful it'll always be, but as firms get better about the practice of data and inference, there are, I find, there's more robust availability for directly from firms if it's not administrative data. So I wouldn't, sometimes it takes some relationship building and getting to know them and for them to get to know your work and trust. and those were, and it's the same thing in the public sector. They can require some investment, but the best panel data sets come directly from the agencies themselves, in my opinion.
So in marketing, based on our research, usually, well, it depends. We can have free and paid data, and we can have consumers and companies in general. So thinking about consumers, the easiest and quickest way is to create your own panel using one of those resources like Amazon Mechanical Turk, Prolific, Crowdflower, or at least 3 of the business that are running this kind of, like you can run your own panel, like inviting people to participate and paying them. But these usually are cheap compared to buying data from, for example, Nielsen, that has their own panel. Some of these big companies, big research companies, they have their own panels. So it's very expensive to buy from them. And sometimes it's easier to make your own panel. The problem is that sometimes it takes a while. You have attrition, and it's hard to maintain people on the panel. So I myself have done panels of 1 year of data, collecting data every 2 months. Usually have 30 or 40% attrition, and at the end, it's sometimes you need to try to at least in the beginning, maybe multiply by 2 the sample you want at the end, in order to avoid statistical power, lack of statistical power at the end. So this is how I would recommend for studying consumers. Studying firms, I totally agree with Jason, and we use a lot publicly available data. We are seeing more and more different ways of data collection, especially for government. For example, traditional ways of collecting data like census are very expensive. They take years to get done, sometimes 10 years. And we are seeing some countries avoiding this type of, or at least using different approaches. Like as I've heard that in the UK, the government is not going to run census anymore, the big census like the ones we are used to. So they are going to collect more regular data from different sources that you can use. Also in marketing, another very useful way is to scrape data using Twitter or Instagram or other social media approach. This is a different way of dealing with. The problem with this data is always privacy issues, and sometimes we cannot control exactly who is doing what. Sometimes it's hard when people do not make their identity public. So it's also hard to follow, to have a good quality panel. So yeah, it's not easy and straightforward to have good panels. This probably explains why we don't see that much this kind of data. Although when we see it, we have usually very good studies, and you increase a lot your chance of getting a good scientific result and therefore publication.
Great, thanks, Vinicius and Jason. And now in the last couple of minutes, I would invite you guys to say some final words, some final takeaway you want people to keep in mind from potentials of use of panel data.
Sure, I think one takeaway that I've had in my short career of doing this is how quickly things change. Right. I think that one approach today, that may have tremendous advantages. We may learn 6 months from now that there are big problems and some of the assumptions not holding, or better approaches. And so one piece of advice that I've learned often the hard way is to try to stay updated. Right. As you to read other people's work and criticisms of that work, because often you may sink a year or more or 2 in an empirical project and learn that approach that you're using is no longer considered a good one. And so to stay updated, I think, and listen and go to webinars like this and read other work would be my piece of advice.
Thank you, Jason. I believe that the gold standard in science is it was and it is and it will continue to be to understand the why of things. So whenever you are able to be updated in terms of methods, in terms of types of data, and analytical approaches to understand the whys or to explain the why more properly, if you manage to do that, you are on the right path. Sometimes it's challenging to do that because, as I've mentioned, for example, to run a panel at Amazon Mechanical Turk, it's easy, it's straightforward, but you are not dealing with real people. You're dealing with professional workers that are answering surveys every day. So you should try to always guide or at least move towards the most real data as you can get in terms of phenomena of explanation, not only in terms of data quality, but also in terms of analytical methods to analyze that data. In this sense, I believe that Jason's paper is a very good approach for those who want to start learning panel data. And I myself, I'm happy to address any questions in case people are interested on machine learning. So I believe that I made sure to include my email on the presentation. So yeah, I believe this would be my final takeaways. And thank you again, Rafael. And thank you again, Jason, for the opportunity to be with you guys here.
Great. And thank you again, Jason and Brei. It was really, I think, really interesting, deep discussion, opening a perspective for what can be done in different approaches, what are the trade-offs between these different approaches, possibilities and limitations. And I think it was very, very productive getting some positive feedback here on the Zoom chat. Thank you again, and hope to meet you soon and hopefully in person. Thank you very much.
Thank you. Appreciate it.
Thank you, guys.
My heart